So if you can turn to the back of your test review packet. Just so I can kind of talk about what we're going to be working towards in terms of preparing for the non-calculator test. First is similar to the problem that you saw on your quiz, where that fractional problem where you have to split up into individual terms and get everything up and rely on power rule. You'll see one of those problems. So just want to make sure that now that we have used substitution, our temptation is our tendency is we want to be able to use that as our first option. But anytime we see a singular term in the denominator, we should always rely on power rule. So even if we see parentheses, this is not going to be a use substitution problem. This is going to be a power rule problem, right? We expand everything out, FOIL everything out, split into individual terms, bring all the variables up, and rely on power rule. Number two, use substitution. We've been practicing a lot with that. So we always want to look to see, can we expand? If we can't expand and rely on power rule, then our next option is use substitution. And our U value is typically what's inside the parentheses. And if we don't see a set of parentheses, we want to rewrite the problem with the set of parentheses. And usually that's converting radicals to rational exponents that can help us get there. And also understanding that even if we see a parentheses around x, we know our U value is never going to be x. I mean, we can do it, but it's never going to help us move forward in the problem. We're just, if we do a 1-for-1 variable swap, we haven't made any progress. So today we're going to look at some trig integrals where we have to rely on unit circle values to arrive at our solution. But we know that anytime we see definite integrals, the bounds are always going to be the last thing we involve, right? We treat the problem like if we don't see any bounds, solve that first, and then we bring in the bounds, half bracket, plug in upper and lower bound. Okay, next up, definite integrals for absolute value functions. We haven't talked about this yet. I'll talk about how we can solve these types of problems. So we'll do that as soon as I get through this list. Even odd functions, hopefully we feel more comfortable with it now that we've seen a couple of examples across multiple days. Second theorem, we did that yesterday, where we know that if we have pairings of derivative and integrals and definite integrals next to each other, we basically are canceling them out and then just working that upper bound into the function. Average value theorem, finding the average height across our graph. That's our average value theorem. Particle motion. If we start at acceleration, we can move back up to the original function by taking the antiderivatives. Basically, the process that you saw on the quiz where you took the antiderivative twice to get from f double prime to f of x, and along the way, plus c's will show up. And then there's no sigma notation, no limit definition on the test. And just like how you did on the quiz, I think this is a good thing to know is, or to put on top of your test is your 6 trig derivative rules, knowing that working backwards from them will just be your trig integral rules. And then also we need to know make sure we review our unit circle values. Okay. Okay, so really the only main thing that, or two things that we need to make sure that we spend more time on is these trig integrals, and then also definite integrals involving absolute value function. Okay, any questions about topics for your test? So your test will be 10 questions. Okay, if you can turn to page 2, I think we did all of page 1. I'm going to have you guys cross out number 6. We're not going to do that problem, but in place of it, I'd like for us to copy this problem down. And we'll definitely practice more with these absolute value functions, but I think once you get a hang of it, it's not too bad. Now, there's 2 ways that we can solve this. I'm not going to show the other way. Typical. We can do this using power rule, but if you want to do this using power rule, you have to write this as a piecewise function. And then you got to do power rule twice, and then you got to split your bounds. I just prefer a more efficient way of going through it. So we're not going to go through rewriting the absolute value function as piecewise and then doing power rule for those. So I'm going to show a different way of solving this problem. Okay. And we're going to do this just using our geometric shapes. So first is we have to understand that we're dealing with the area, where we're trying to find the area of a region, but we're not going to rely on power rule. So first is just understanding what the graph looks like. Okay, does anyone know what absolute value function looks like? Yeah, has a V shape, right? So that's, and the benefit of that V shape is that it's going to create these nice geometric shapes that a curve would otherwise not. So what's going to happen is because of the way that these graphs are shaped, we're going to be able to see these triangles form, and we're basically just going to be adding areas of triangles because of the way that the graph is going to form with no curves, and this is going to create a nice geometric shape. But we have to know how the graph is. So whatever causes that expression to be 0 is going to be where your vertex is. So your vertex can be found by setting the expression equal to 0, or at least what's inside the absolute value equal to 0. So here, x minus 2 is equal to 0. Therefore, x is equal to 2. So that x equals 2 tells you where the vertex of your absolute value function is going to live. Okay. So once you know where that vertex is, then you're going to identify that point, put a dot at that order pair to 0. And this is basically the vertex of your graph. So you don't have to worry about, how what your slope is, as long as you just create a V-shaped graph from that point. You basically have the graph in front of you. And we just have to be able to extend the graph as far left as -2 and as far right as 3. And again, you have to be accurate, just enough for us to, we're going to find order pairs later that can help us find the dimensions, but we'll just try our best to. Okay, so when we go from -2 to 3, notice that, and then from where these points land, you're going to do a line to indicate that we're just going to be looking at the shaded region between -2 and 3. And if you shade these regions in, remember, we only look at what's between the graph and the x-axis. You're going to see 2 triangles form, and basically we're just adding the areas of these 2 triangles, and that will get us that depth integral value. Okay, now we're going to go ahead and find these order pairs, because these order pairs will help us identify the dimensions, the height of our graph. So this graph is y equals absolute value of x minus 2. Okay, so if I plug -2 in, I can find the y value there. If I plug 3 into the function, I'll get the y value there. And the y value will also tell us how high the graph is above the x-axis, which will tell us the height of these triangles. So if I plug -2 in for x, what do I get? What's the absolute value of -4? 4. So this order pair here, I'm going to say -2, comma 4. I'll put a circle around that 4 to indicate that's the number that I really care about, because that 4 indicates the height of this triangle. Okay? If I plug 3 into x, what do I get? 1. Absolute value 1 is still 1. So the order pair is 3, comma 1 is the y value that I care about. And that's going to be my height. Okay. All right. What's the area formula for a triangle? 1/2 base. Yeah, 1/2 base times height. So we just have two triangles to worry about. The height of this first triangle on the left is height of 4. And you can also count here, what's the base of this triangle? Also 4. So my first triangle is just 1/2 base times height, 1/2 4 times 4. Okay, what's the height of this smaller triangle on the right? 1. What's the base? 1. 1/2 1 times 1. So put this together, 16/2 plus 1/2, 17/2, or 8.5. And that's it. So you're going to sketch your graph, create your two triangles, find the y values at the points, at those endpoints. Those will act as the heights, identify the width by counting, and then 1/2 base times height twice. That'll get you to the area. Yeah.
How do we know what the graph looks like?
Oh, so your graph, your vertex is always going to be your starting point. The middle point is always going to be whatever causes that to be 0. And once you have that middle point, you just extend the graph.
Okay, and that's only for absolute value.
Only for absolute value, yeah. And they'll always look like this. Okay, we'll get some more practice with this, but for now, are we okay? Okay, let's go to let's see, I think yesterday. I don't think I got to numbers 9 and 10. So let's do numbers 9 and 10 on page 2. Okay, we know that anytime we see bounds, it's never going to be the first thing that we involve. What does this problem look like to you? Yeah, power rule, right? Only one term in the denominator. We don't want to go through use substitution, especially if something can just be split up and relied on with power rule. So we're just going to focus on working on our indefinite integral. And then we can worry about the bounds at the end. So I'm going to begin going through that cleanup process, trying to get my denominator split up or my fraction split up, bringing all the variables up to the top, and then my eventual power rule. Okay, subtract exponents, right? These terms are not ready for power rule. So 1 minus 1/2 is half. Bring this variable up to the top. Both terms are now ready for power rule. Get these denominators cleaned up. And now we're ready for our bounds. Okay, upper bound first. Minus big parentheses, and work in the lower bound. So technically, we can leave our answer in this form, but I do want to have us practice working these numbers down from these rational exponents without a calculator. Sometimes we look at this and it feels intimidating, like raising 9 to the third power and then taking the square root. Right? That feels like that could take a long time to do. But there's a shortcut to this. We don't have to take that 3 first. We can deal with the 2, and that 2 means what? Square root, right? That gets a lot easier. What's square root of 9? 3, and then 3 cubed is 27. So that feels a lot easier to do rather than trying to figure out 9 cubed, get that huge number, and then trying to figure out the square root. And that's going to be hard to do without a calculator. But
we can leave our answer.
Yes, but I do think this is important. This is a nice skill to have. Imagine a multiple choice question that cleans it up all the way, and you have a calculator. Okay, so I just want us to practice working that exponent, even though if it's free response, you can leave your answer unsimplified. Okay, so here square root of 9 is 3. Here 4 to the third is not too bad, but it's easier to make the square root of 4 2, and then 2 cubed 8. And then here that's just square root of 2, which is square root of 4, which is 2. So I'll accept any of these options, but I just want to make sure that we know how to do this process without a calculator. Okay, number 10. Okay, so the first thing that we need to understand with depth integrals is that the power of 3 and 0 are not going to be involved with this expression, right? The bounds are always the last thing. We have to figure out what the in-depth integral of this is before we can involve the bounds. Now, we know that integral rules start on the right, moves to the left. Do we see a rule that we can use? Yeah. This is use substitution. I think what I see some students do is they find creative ways to apply rules here, and they say, well, I have secant tangent here, so why can't I just make it secant squared tangent squared and turn that into secant squared? So our integral rules is very restrictive. If it's not exactly the same as what you see here, we don't have a rule to use. So we can't adapt the squared to this and then just say, oh, integral secant squared tangent squared must be equal to secant squared. I just square both sides, and that will give me my integral. My integral rule only works if it matches perfectly. So the first thing I want to see is that there are no rules that matches with what we see in front of us. Okay, and if we don't have a rule that is matching with our available trig rules, then we have to rely on use substitution. So if we want to rely on use substitution, we prefer to see some parentheses. Where can we create parentheses in this problem? Yeah, around tangent of x and also around what? Secant of x, right? And that gives us two options. And we have to be able to choose the correct option. But rather than going down, just guessing and going down the wrong path, we can kind of predict what's going to work and what might not work. If our u value is secant of x, for instance, what's the derivative of secant of x? Secant tangent, right? Do you see a secant tangent elsewhere in the problem? Not perfectly, right? We see a tangent squared. There's a leftover secant here, but it's not going to match up perfectly, right? So our u value being secant may not be a good fit. What if our u value is tangent of x? What's the derivative of tangent of x? And we do see secant squared elsewhere in the problem, so that should be a better fit. So if you're ever deciding between two u values, think about that u value's derivative. And if you see that variation of that derivative elsewhere in the problem, that's usually a good indication that we can get things to fit and cancel out down the road. Right, so let's work on our u value being tangent. So as soon as we identify our u value, we're going to move into our derivative, du dx equals secant squared x. Cross multiply. Make our substitutions. Remember, whenever you rewrite your problem, you're only replacing what you've underlined, but everything else you're going to bring back and see what's going to happen after that. Okay, dx gets replaced with du over secant squared x. All right, what do you see? That's a good sign, right? We can't move forward with u substitution unless all the x's go away. Do we have any leftover coefficients? Okay, so it's just integral u squared we have to worry about. So we should be looking at a simpler version of the problem that we started with, which we are, and all the x's are gone. Okay, so really the only thing that we need is power rule. U squared becomes u cubed over 3. What should we do before we work the bounds in? Yeah, let's bring it back in terms of x. Now, again, your two options here. If you want to keep it in terms of u, that's fine, but you have to convert these bounds in terms of u. But I think most of us prefer just to leave it in terms of x and just rely on the original bounds. So we have our antiderivative. Sorry, let's bring back our x variable. I'm going to rewrite it as 1/3.
Would the du not turn into plus c?
Yes, but why do we not worry about plus c? Because there's bounds, yeah. So the plus c, it's there, but it ends up getting canceled out. So we never have to worry about it if there are bounds. If there are no bounds, then we will do plus c. Right. What's next? Oh. Hop valley gets plugged in for x. And then what comes after? Okay, but what operation do you put here? Minus, yeah. So I'll make sure we understand it's always going to be a minus. Right, we plug the values in. Can we leave our answer like this? No, we got to go one step further. Okay. I know previously we could leave our answer like this because these are numeric values. These are not numeric values. You have to get it at least down to a fractional value using unit circle value, and then you can stop. But we can't leave these tangents and sines and cosines. And the same goes for the AP exam. They're going to dock off points if you leave your answer like this. You got to go one step further before you can stop. Okay, so at pi over 3, my order pair is 1/2, 3/2. Tangent is sine over cosine. So I know my tangent pi over 3 is going to be √3/1. Tangent is 0, it's just going to be 0. Now this is okay. If you leave your answer like this and not go any further, you will not lose any points. But if you were to clean this up, it'll get you down to √3, which is also acceptable. Okay, we're gonna do some more review here, but I just want to give you a preview for tomorrow. So tomorrow, you guys all still have this packet, right? This part 2 packet. We haven't done page 22 yet. So this is particle motion. This is not going to be on the test, but this is going to be on the calculator portion. So tomorrow, I do want to spend some time going over this. So I just want to make sure that you have this packet handy tomorrow for us to get into it. I didn't do this yet because I wanted to cover all the non-calculator portion first and then come back to the calculator portion. So we still need to do this particle motion. Just make sure you have this packet handy. We'll cover this. We'll split our time tomorrow between review and begin to do some stuff for the calculator portion. Let's see. It's through okay, page. Yeah, page 9. Okay, back to average value theorem. Okay, we need to memorize this formula here. But we can start putting everything in, right? Our A value is 1, our B value is 3, our function is the expression provided. We do a little bit of cleanup here, make this 1/2. Okay, so once you've set everything up here, what's the first thing that you're going to focus on trying to do? Yeah, got to do this integral of this expression first. The bounds are not going to be involved. You can distribute that 1/2 through if you want at the beginning. Again, my preference is I like to wait till the end, but it's up to you. You can deal with the 1/2, but the bounds 1 and 3 are not going to be involved. So I'm just going to focus on the expression here. Now, there's only one term in the denominator. We do see a set of parentheses, but we know that anytime there's a single term in the denominator, it's going to be a power rule problem. I'm going to distribute that parentheses through and start to get ready for my power rule that I'm going to apply. X's cancel out. I'll bring this X up to the top. Okay. My terms are both ready for power rule. 4 becomes next term, 4x to the -1 over -1. Let me do some cleanup to make it a little bit easier for me to plug in. Just cleaning up my terms here. 4x is fine. I prefer that x in the denominator so that I don't have to deal with a negative exponent. But now I'm ready for my bounds. Upper bound gets plugged in first. Minus the lower bound. All right. Let me clean this up here. So this is the same thing as 12 minus 4/3. Actually, I don't have to do this right. That 4 minus 4 is a 0. Okay, I'm just going to wipe this out here. So the result of my integral is for 32/3. I don't want to forget about that 1/2, so I'm going to bring that 1/2 back into my calculation. There's also part B. Part B says find the C value. That's basically the X value of our solution. So this is basically our Y value. We take this with the original function, plus 16/3 in for f of X, and then we're just trying to solve for X. I'm going to cross multiply here just to get all of my fractions resolved. Distribute the 3 through, combine like terms, divide by 4, take the square root, plus or minus shows up. Are both valid solutions? Okay. Guess what? Yeah. Because my interval is, yeah, from 1 to 3. So we know negative root 3 is not going to fit our bounds. Okay, number 2. Number 2, we're asked to find the derivative of a function that has a definite integral in it. We're going to have to rely on second theorem. Okay, so I know I want to find the derivative of this expression. And the fact that I have derivative and integral notations next to each other, I can just basically cancel them out and just worry about my variable upper bound with my expression. But something that I should do to maybe help rewrite this. What do you notice here? Yeah, let's get the bounds to be in their right places. We prefer our upper bound to be variable, our lower bound to be a constant. So I'm going to flip the bounds. If I flip the bounds, what needs to happen? Yeah, I need to make the expression negative so I can make sure I balance the change I made. So visually, if it helps you, you know that these operations will cancel out. You just have to worry about how to involve the upper bound with the expression. So first thing you do is just plug that upper bound into the expression. Everywhere you see t, go ahead and replace with that upper bound. And then once that expression is complete, then separately multiply by the upper bound's derivative. So this plugs in for the t times what? If you don't clean this up, that's fine. I'll accept that. So I'm going to be asked to find the derivative of this expression. What's different about, we're still using second theorem, but what's a little bit more involved about this? Yeah, 2 variables. So we got to repeat the process for the upper bound and for the lower bound. So here's the variation for second theorem. Upper bound gets involved with the expression, but then lower bound is also a variable. So put a minus sign after that, and then repeat the same process for the lower bound. Again, if it helps with notation, you can cancel these notations out, knowing that you're only having to work with the upper bound and the expression you see in front of you. In this case, both bounds with the expression, but we're not going to do power rule, integral, derivative with this expression. This is not going to change. X to the 1/2 becomes 1/2 x to the negative 1/2. That's my f of p of x times p prime minus f of q of x. Just going to do a little bit of cleanup, but
How is it negative 6x squared?
negative 6.
Oh,
Excuse me. Oh, square. Sorry, I keep misreading my. This is fine. Okay, next up, let's finish with even and odd functions. Okay, first thing we always want to pay attention to is, are the bounds in the proper order that we would like? Are we going from left to right? Okay, so this is good, right? We don't want to go from right to left, because then the number that we see is going to be easily misinterpreted. So both of these looks like is in the proper order. Okay, which region do we want to build first? Shorter interval first. Not necessarily the fact that it's smaller area is not that important. It's the fact that we want the shorter distance between the bounds. Okay, it's an even function. We're going to go ahead and fill out the other side. Also positive 2, because even. We know that the region from -3 to 6 is a sum of terms. It's not, we don't want to overlap that entire region and call it -4. We're going to put off to the side and know that, okay, there are regions that are already complete. There are regions that are still yet to be completed, but we know that when everything is said and done, we want the regions to add up to be -4. So I have 4, 2 and 2 showing. So what must this region be in order for us to add up to be -4? -8. So I want this region to be -8 below the x-axis. And that's -8. Then this side is also what? Now we can add these values up. Okay, no homework, but I am going to check pages 1 and 2 tomorrow. This is basically what we did yesterday in our Zoom session, our team session, as well as what we did today in class. So if you did everything that we did, then really no homework, but I just want to check pages 1 and 2, what we got. All right, I'll send out a reminder this afternoon. So tomorrow, make sure you bring your other packet, your packet 6B. We'll split our time between reviewing and start looking at the particle motion that we need for calculator portion.
Don't put the phone. That's my bird. Huh?
You still need the.
What? Famous woman's